In day 2 of section 5.3, we're looking at angle bisectors in a triangle. What happens when you construct the 3 angle bisectors in a triangle? We're going to find another point of concurrency with some special properties. So the first thing is that this construction will take place in class, or already has. We're going to find the point of concurrency where the 3 angle bisectors meet. And the theorem is here that angle bisectors in a triangle are concurrent, and they intersect at the point, their point of concurrency is called the incenter. That's the point of concurrency of the 3 angle bisectors, a point that is blank from the blank of the triangle. Let's talk about what we already know about angle bisectors. We know from what we did yesterday that any point on an angle bisector is equidistant to the sides of the angle. Because if you're on the angle bisector, you should be going through the middle of that angle. So you should be the same distance to the 2 sides. So in this case, this blue line is an angle bisector of angle B here. So this incenter, where all 3 angle bisectors met, should be the same distance to the sides of the angle as long as we're measuring at or going at a right angle. And I already have the points out here that are at a right angle for certain. So I know that going at a right angle to the sides, these 2 segments are congruent. Let's take a look next at the green angle bisector. Well, if this green line is an angle bisector as well, then this incenter, any random point on the angle bisector, should be equidistant to the sides of that angle as well. And the sides of angle C here are here and here. I already did a right angle to this side, but I do need to do a right angle to this side. And again, we know if we're on the angle bisector, we should be equidistant to the sides. I already put 1 tick mark here. 1 tick mark goes here. And finally, this red angle was another angle bisector, therefore this point should be equidistant to the sides as well. And actually, I could have marked that these angles are congruent. The blue line's an angle bisector. These angles are congruent because this green line was an angle bisector. And finally, these 2 angles are congruent because the red ray is an angle bisector. So this incenter, oh, it's blank from the blank. We just talked about how the incenter, or any point on an angle bisector, should be equidistant to the sides of an angle. So in this case, we're equidistant to the sides of the triangle. So the angle bisectors of a triangle are concurrent. They meet at this point called the incenter. That's equidistant to the sides of that triangle because any point on an angle bisector is equidistant to the sides of the angle. So this leads us to some cool properties of the incenter. We're kind of summarizing everything here. Again, the incenter is the point of concurrency of the 3 angle bisectors. It's where they meet in a triangle. You know how we had done in the last section was perpendicular bisectors, and those could be located in the triangle or on the triangle or outside, but the incenter is always inside the triangle no matter what. And we talked about in the previous slide here how it's equidistant from the sides. In this case, from the incenter, these segments from the incenter to G and to F and to E, those would be my equidistant segments because these are the distances to the sides at a right angle. I just don't have the right angle marked. If I asked you which lines are the angle bisectors, you should tell me that these red lines are the angle bisectors. Because you can tell that they are going through the middle of each angle. This is bisecting angle C, this is bisecting angle A, bisecting, cutting in half angle B. And those blue lines are the distances to the sides. The incenter is equidistant from the sides of a circle, so I marked them all congruent there. And then the coolest thing here, because the incenter is the same distance from the sides, I can make a circle where this distance is the radius of that circle. And so the incenter is the center of the inscribed circle. That word inscribed means it's inside it's a shape inside another that touches all the sides. And you notice this is an inscribed circle. It touches all the sides of the triangle. Let's take a look in Geometry Sketchpad here. So I have a triangle in this case. I have found the incenter by doing all of these red rays are the angle bisectors. Located the incenter. and I'm showing you the distance to each of the sides, and right now all those distances are the same. I'll bring this up here. They're all 4.8. If I grab a vertex, and if you watch the numbers, they're always the same distance. They'll change together. That circle, this inscribed circle, is always touching at the points that are perpendicular to the side. The distance from that point to the side. And the incenter has to be inside that circle, seeing it's the center of the inscribed circle. So the incenter is awesome. Center of another circle, this is the inscribed circle. Because it's equidistant from the sides, it will touch all three sides at one point. So we got all our properties of the incenter, and I have one example for you to look at. Find GW if G is the incenter. Okay, if G is the incenter, I know the incenter is equidistant to the sides, which these three blue segments are all the distances to the sides. I know those are the same. So seeing one of them is called 2x, all of these are 2x as well. The angle bisectors, I know that angle bisectors had to be found or constructed to locate the incenter. And the angle bisectors are in red. You can tell that they are definitely cutting these angles in half. Well, how am I going to find GW? Isn't GW the same as this 2x? Since that was the incenter at point G, it's equidistant to the sides, so all three of these blue segments are 2x. But now I need to find this. I know we have the angle bisector length from G to the vertex was 25. 24 is length here, and I have a hint. Use Pythagorean theorem, which says that in a right triangle, one leg squared plus the other leg squared equals the hypotenuse squared. So let's use Pythagorean theorem, because if you notice, because of the fact that the distance from G to the side is at a right angle, I have a right triangle here. Now one leg of the right triangle would be 2x, so I have to do 2x quantity squared. Be careful, I'm going to have to square 2 and x. Plus the other leg of this right triangle would be 24, because it's touching the right angle. So plus 24 squared equals, hypotenuse of this right triangle is opposite from the right angle, or 25 squared. Let's solve for x so that we can find the length of GW. Now 2x squared, I have to do 2 squared, which is 4, and x squared, plus 24 squared is 576, equals, and 25 squared is 625. Subtract 576 from the 625, and we get 49. Divide by 4, and actually, instead of getting a decimal, I'm just going to write 49 divided by 4. Reason why? Because this is x squared, and I know to undo squared, I'm going to take square root. And I know that 49 and 4 are both perfect squares, so I might as well just leave them that way. And I know square root of a fraction is square root of top and bottom. Square root of 49 is 7. Square root of 4 is 2. So x is 7 halves, or 7 divided by 2 is 3.5. And I've got x, so I'm like 98% there. I was supposed to find GW. And notice that GW was 2 times x. And since x is 3.5, 2 times 3.5 is 7. So 7 squared plus 24 squared equals 25 squared. We've found the length of GW. Using the fact, again, in center is found by constructing these angle bisectors in red. The incenter is equidistant to the sides. And again, it's the center of the inscribed circle that would touch all those sides. So using properties of the incenter where the angle bisectors meet in a triangle today.